9.10 Lesson 7 Taylor and Maclaurin series. Our objective for today's lesson is you'll be able to use the binomial series to find Maclaurin series, which are Taylor series centered at 0, to find Maclaurin series for functions such as f of x is equal to 1 over the square root of 1 minus x, and f of x is equal to the square root of 1 plus x squared. Vocabulary, binomial series. So in yesterday's lesson, using the definition of Taylor series, we formed this Taylor series centered at 0 from the function 1 plus x to the k, and it can be shown that this Taylor series will in fact converge to the function from which it was formed on its interval of convergence. The convergence at 1 or negative 1 depends on the value of k. So that's what we did yesterday. And this is called the binomial series. Yesterday we also looked at this problem where we have the function f of x is equal to the square root of 1 plus x, which we can of course write as 1 plus x to the 1/2 power, so that it is written in the form 1 plus x to the k. And we looked at how we can use the binomial series to write a Maclaurin series for the function f of x. So we simply note that the k value we have is 1/2, and in the binomial series we replace k with 1/2. And yesterday we discussed the simplification from one step to the following step. And then finally, we also looked at how we can represent the series with summation notation. And we left out a couple of terms because it was more convenient for us to observe a pattern that holds for all terms, starting with this term, which was the third term, starting at n is equal to 2. And we also discussed that we had to describe what was going on in the numerator here by observing a pattern that we see as we go from one term to the next. So the factors that we have in the numerator will be of the pattern 1 times 3 times 5, and continuing until we get to 2 times n minus 3. We just reviewed what we did yesterday because we're going to use that to make what we're doing today easy. Today's lesson is not new because we've done this before. For example, if we wanted to write a power series for sine of x squared, what we did was we looked at the power series for sine of x, and we just replaced wherever we just replaced every single x with x squared. The only difference between that and what we're doing today is we're going to be doing the same thing, but for binomial series. So from our lesson objective for today, we have this particular function that we'd like to represent with a Maclaurin series. You should recognize that we can easily manipulate this function so that we can represent it with a binomial series. And what we can look at is the square root, and we can easily rewrite that as to the 1/2 power. So we have 1 plus x squared to the 1/2 power. So now we have something that fits the form 1 plus x to the k power. We have, instead of 1 plus x, we have 1 plus x squared to the k power, where k is equal to 1/2. And we already took care of this function yesterday, where we had 1 plus x to the 1/2, k was equal to 1/2, and of course, for the binomial series, the function that we derive the binomial series from is 1 plus x to the k. So yesterday we had exactly the same base as the function from which the binomial series was derived. We had 1 plus x, and k was 1/2. So all we had to do was, because the base was exactly the same as the base of the function from which the binomial series was derived, all we had to do was take the k value of 1/2 and substitute for k wherever we saw k in the binomial series. And we did that yesterday, and this is what we came up with. I want to use that to help us with the problem that we are working on now, because the problem that we're working on now is right here. The only difference between this and the function from which the binomial series was derived is, instead of having 1 plus x to some power k, I have 1 plus x squared to some power k. In this case, my k value is 1/2 because I had square root. But that's the difference. The difference is, instead of having 1 plus x for the base of my function, I have 1 plus x squared. And that's why I mentioned the problem that we had done earlier about trying to represent the function sine of x squared with the power series. How did we do that? We looked at the power series for the function sine of x and just replaced every single x with x squared. So what we can do today is take advantage of our work from yesterday to make our work easy. So we had already done the problem of representing the function f of x is equal to 1 plus x to the 1/2 with the Maclaurin series yesterday. We used the binomial series and just replaced k with 1/2, and this is what we came up with. And we were able to do that because the base of our function from yesterday matched the base of the function from which the binomial series was derived. Now notice that for our function today, we also have k is equal to 1/2, so we can take our work from yesterday, but the only difference between the function from yesterday and the function for today is, today the base of our function is 1 plus x squared. Basically, the difference between what we have today and what we had yesterday and the base of the function from which the binomial series is derived is, I have x squared in place of x. So just like we dealt with sine of x squared, we're going to do the same for this function. We're just going to take the power series for 1 plus x to the 1/2 and simply replace every single x in that power series with x squared. So we're just going to take the power series for 1 plus x to the 1/2 and replace every single x with x squared to get the power series for the function. F of x is equal to 1 plus x squared to the 1/2. So we will have 1 plus 1/2 x squared, and then I can just take the sigma notation from yesterday. Everything is the same. The only thing that's different is, instead of having x to the n, I'll have x squared to the n. So 1 times 3 times 5, 2n minus 3 over 2 to the n times n factorial. So in place of x, I will write x squared to the n power. So I have x squared to the n power. Now if you choose to, you can rewrite that, because what you have here is the power of a power. So when you multiply the exponents, you would get x to the 2n. So here's our second example. The first thing that we must do is to rewrite our function so that it would be in the form 1 plus x to the k power. So we can do that by using algebra. we can write the square root as to the 1/2 power, so we will have in the denominator 1 minus x to the 1/2. And we know that with powers, if we take a power from the denominator to the numerator, the sign of the exponent will change. So what we can do is we can write this as 1 minus x to the negative 1/2 power. It is almost in the form 1 plus x to the k power. The only thing that I need to do is to take care of the fact that I need to have 1 plus something. I have 1 minus x, but I can write that as 1 plus negative x to the negative 1/2 power. So what I have accomplished is I have rewritten my function to be in the form 1 plus some function of x to the k power. And that's what you'll have to do for the homework problems tonight. For example, number 17. Your first step would be to algebraically manipulate your function for number 17 until you can make it fit the form of 1 plus some function of x raised to the k power. So I've done that with this example. I have rewritten our function as 1 plus negative x to the negative 1/2 power. Having done that, I'm able to represent my function with a power series. So I write 1 plus k is negative 1/2 times x plus k is negative 1/2. So I'm working with this right here. And then k minus 1 would be negative 1/2 minus 1 would be negative 3/2 x squared over 2 factorial. And then I have negative 1/2 for k, negative 3/2 for k minus 1, and negative 5/2 for k minus 2, x cubed over 3 factorial, and so on. So what I'd like to do is simplify that using patterns that I notice. So 1 minus 1/2 x. And then here, if I multiply the two negative factors, I'll get a positive factor. And then I have 1 times 3. And then I have 2 times 2, or 2 squared, divided by 2 factorial, which is the same as multiplying by 1 over 2 factorial, x squared. And then here I have a product of 3 negative factors, so my term will be negative. And then I have 1 times 3 times 5. So I have 1 times 3 times 5. I also have 2 times 2 times 2, or 2 to the third, divided by 3 factorial, which is the same as multiplying by 1 over 3 factorial times x cubed. And if I were to do one more term, I would see that that term would be positive. And what I will be doing is I'll be doing k times k minus 1 times k minus 2, which I already have here. But then I will also be doing k minus 3. So that's going to be negative 1/2 minus 3, which will give me negative 7/2. So what that will do is I will have 4 negative factors. So when I multiply them, I get a positive term. And then I have in the numerator 1 times 3 times 5 times 7. And I will have 4 factors of 2 multiplied by the reciprocal of 4 factorial. And then that would be 2x times x to the 4th. So that pattern continues, similar to what we saw yesterday. And if you wanted to describe that using sigma notation, all you would have to do is the following. You're going to write 1 minus 1/2 x. And then you can start with your sigma notation here, starting at n is equal to 2, going to infinity, and I will have negative 1 to the n power There is something that I forgot to do, and I'll tell you what that is. But I guess I'll just finish with what I have so far so you can see the adjustment that needs to be made. So the pattern in the numerator is the same as what we saw yesterday. So we have 1 times 3 times 5. When do we stop? We stop when we get to 2n minus 3. So for example, here we stop at 5. 2 times 3 is Actually, it's different from yesterday, so we don't, it's not 2n minus 3. It would instead be 2n minus 1. So if you look at what we have here, we stop at 5. So n is 3, 2 times 3 is 6, 6 minus 1 is 5. Here we stop at 7, n is 4, 2 times 4 is 8, 8 minus 1 is 7. And here we stop at 3, n is 2, 2 times 2 is 4, 4 minus 1 is 3. So we are taking care of the pattern, so there's no problem there. And we took care of the alternation of the signs. So now we have to take care of the denominator, which is of course 2 to the n times 2 times n factorial. And then you have x to the n. That's the part that I neglected to take care of, because you know that our function is actually 1 plus negative x to the negative 1/2. So I had no issue taking care of k is equal to negative 1/2. I've been doing that step by step. But the one thing that I forgot about was that I have not 1 plus x in the base, but 1 plus negative x. So what that means is each of these x's should actually be negative x. So that should be negative x. So that should be negative x squared. That should be negative x cubed, and so on. So what effect does that have? Well, it would change the sign here from 1 minus 1/2 x to 1 plus 1/2 x. And then it would also have some effect on the description of the nth term. And I can see that most clearly just by working with the nth term as I have written here. So I'm going to replace x with negative x and raise that to the n power, and then I can work with that and I'll get the correct description of the nth term. To be correct for the step before, I need to replace every x with negative x. And here I will have x to the 4th replaced with negative x to the 4th. So you can see that nothing really changed, except I replaced every single x with negative x. And when I do that, the second term becomes a positive 1/2 x. And the description of the nth term, you can get the correct description just by looking at negative x to the n, which you can write as negative 1 to the n times x to the n. And the effect that has is the following. You have a product of two powers with the same base, so you can add the exponents. N plus n is 2n, so you have negative 1 to the 2n, and for any n, 2n will be even. So negative 1 to an even power will give you positive 1. So I can see what effect the negative x had. Basically, it's going to make all of the terms of my series positive. And you can see that in my work. Now, because of some mistakes that I'd made earlier, maybe it doesn't show up the way it's supposed to correctly. So let me just fix that. Actually, everything that's on screen is correct. It's just that if you wanted to simplify the line prior to the last line where we have summation notation, what you would do is you'd go ahead and do, for example, negative x squared, which will give you just x squared. And then here you have negative x cubed, which would give you negative 1 times x cubed. And this term was a negative term, but now you have negative 1 times x cubed, so that becomes positive, and this becomes just x cubed. And then here you have negative x to the fourth, which is just x to the fourth. So I didn't have anything that I needed to change. It was just a matter of simplification. But what I had forgotten at the outset was I forgot the fact that I have 1 plus negative x to the k power instead of 1 plus x. And for that reason, in the binomial series, I needed to replace every single x with negative x. But this is correct, and what we have is basically a series where all of the terms are positive. Unlike our example from yesterday, we could also include the second term as a part of our description of the general nth term, and if we were to do that, our index would start at 1. And the reason why we can do that is because the pattern of the factors in the numerator can be described for the first, for this term here, 1/2 x, where we only have 1 in the numerator. So if n is 1, 2n minus 1 would be 2 minus 1, which would just be the single factor of 1 that we have for that term. And in the denominator, we would have 2 to the first, which is 2, times 1 factorial, which is, of course, just the 2 here. So we could include this term in the description of the nth term, get rid of that term, and start the index at 1, and that works as well. So our objective for today is using binomial series to find Maclaurin series for functions such as the ones from our example for today. But generally speaking, if you have any function, to be able to use the binomial series, you have to algebraically manipulate your function so that you will have 1 plus some function of x to the k power, because the binomial series is derived from the function 1 plus x to the k.